Let's go. Okay. 118. A particle has shifted along some trajectory in the plane xy from point 1 whose radius vector is given, okay, to point 2 radius vector. This thing, during that time the particle experienced the action of certain forces, one of which being this. Okay, find the work done by the force F. Here R1, R2 and F are given in SI units. Good. This is the force is constant. Well, that's very nice. So the displacement vector is just 1 comma -5, right? So it's gonna be 1 comma -5 that dot 3 comma 4. So 1 times 6 is 3, and then -5 and 4 is just -20. So it's gonna be -20 plus 3, which is -17. So 118 -17. This was easy. 119. Locomotive of mass m starts moving so that its velocity varies according to the law. Okay, where a is constant, s is the distance. Okay, whatever. Find the total work performed by all the forces which are acting on the locomotive during the first t seconds after being in motion. Okay, after the beginning of motion. Fine. So t seconds, and you want the work done by all the forces which are acting on the locomotive force. I mean, come on, it's just the acceleration and all that stuff, right? Hey, wait a second. Oh, so the total work done by all of the forces acting on it, that's just the kinetic energy. I mean, the change in the kinetic energy. So initially it is equal to 0, its velocity is 0, and then finally when it is, yeah, right, it's doable. So this thing, it is the velocity, of course. I mean, they give us a speed basically, and we know that this guy, speed, I mean, it's just ds upon dt, right? Exactly. So all you got is just, well, s power -1 upon 2 ds is equal to a dt, and then you can integrate to get what s is. So this will be, so plus 1 upon 2 square root of s is equal to a times t, because s initially is 0. Now once you know that, you can just plug that in here. So you will just get v is equal to, oh, in fact it's like v squared is equal to a squared times s. Okay, whatever. Thing is that, yeah, like v will be equal to so a squared s is like a into a t upon 2, so a squared t upon 2, that should do it, I guess. Yeah, exactly, because it was like v squared minus u squared is equal to as, and then it's kind of similar and whatever. So in first t seconds your velocity will become this thing. So what is the work done in the first? It's half mv squared, so half m, this thing squared is just a power 4 t squared upon 4, and that's what it is. M a power 4 t squared upon 8. Next, 120, I think. Kinetic energy of a particle moving along a circle of radius capital R depends on the distance covered s as this thing, where a is a constant. Okay, so it's moving along a circle, huh? Find the force acting on the particle as a function of s. Oh, okay. Fine. So that's nice. Kinetic energy depends like that, huh? And as a function of s. Wait a second. It's like, wait, if it's just moving on a circle, right? Then its displacement, I mean, the distance divided is just, well, r times theta, right? Exactly. So basically, what you're seeing is the kinetic energy is just a r squared theta squared. Yeah. So wow. Okay. What we want is the divergence of this. Okay, you don't, sorry, the gradient of this thing, but you don't even know what gradient is. So like that will be hard to tell you. Actually, we don't know what happens when it. Yeah. Wait a second. Huh. Fine. Fine. The kinetic energy does actually depend like that, huh? So since distance is traveled, it's moving along a circle. Yeah, so it follows this equation. That's good and all. We don't want this thing. Look, I made a whole video on how to get curl in what do we call it? In the polar coordinates and cylindrical coordinates and that stuff, right? So in this particular case, we are still going to do the same thing. We just figure out what the tangential force is, I guess. Or you could just figure out what v square upon r is and all that stuff. Uh-huh. What really happens when this increases? So, oh, come on. It is going to be integration. Okay, no, don't do it. Just figure out the velocity and everything. Yes, that will be much better to do. So the kinetic energy is half mv squared, right? And since it's moving along a circle, it's always moving tangential to it as well, right? Okay, as squared. First of all, let's figure out something. What this means is like mv squared, like v squared is equal to. Okay, let's not go with that. Just divide by radius, right? So it's got mv squared upon r is equal to 2as squared upon r. Well, that's going to be the centripetal force. And now we also want the tangential force. So the tangential force, that times the ds vector, right? That is in fact the work done on the particle. So that will just be equal to, like, yeah, half mv squared derivative of that thing. So mv dv upon, wait, what? Oh, yeah, like an element of work done basically. That's what we're looking for. Okay, so you can just go with, like partial derivative with respect to s. So partial of, it's getting complicated, right? Yeah, it's not worth doing it. F tangential times ds. That's the work done on this, which is the change in kinetic energy. So, oh, in fact, it's not that bad actually. It's just dv. It's not derivatives or anything. It is going to be mv dv. There we go. Good. Yes. And now the thing is, we know what v squared was, right? So you had this thing. So in fact, it's just, yeah, like the kinetic is just as squared. So you can just differentiate that thing as well. So you just have 2as ds. Why not do it like that? Better, I think. But that means it's like tangential force is just 2as. Oof, that's nice. Now you know tangential force, you also know the centripetal force. So now we have everything and we can figure out what this should be. Yes. What was I talking about? What our total force should be. Or maybe you should just write this as a vector. Yeah, writing as a vector will be better. So I'll write it like that. So the force is, first of all, sum in the radial direction. So 2as squared upon r, negative of all that stuff, because just v squared upon r, usual. Huh. Yeah. And that times r hat. Okay. And then plus this tangential force 2as times t hat. Well, that should do it. Next question. 121, huh? Body of mass m was slowly hauled up the hill figure 1.29 by a force F, which at each point was directed along a tangent to the trajectory. Well, that's really nice. So F, okay, it's just tangential force. That's what you're saying. So like, fine. Find the work done. They don't capitalize capital. Why did they bold? Why is this bold? Anyway, maybe they're just using bold F a lot and then they somehow, yeah, I get it. Find the work performed by this force if the height of the hill is h, the length of its base is l, and the coefficient of friction k. Wait, what? But this trajectory in itself, okay, this is bad. Wait, slowly hauled up. Okay. Now I understand what's going on. So there's this force acting on it. At the same time, there's also gravity acting on it, normal force. Well, normal force does no work. Gravity does work of mgh. Actually, I should say negative mgh because it's pulling towards yeah. So negative mgh plus whatever the work done because of this force is, well, those combined, those should be a change in kinetic energy, but that's zero. It's slowly hauled up. So yeah, it's stationary over there and also over there. So kinetic energy is 0, work done is mgh. No problem. Right, next. 122. A disk of mass m is equal to 50 g slides with the zero initial velocity with the zero, okay, with zero initial velocity down an inclined plane set up an angle alpha is equal to 30 degrees horizontal. Okay, a disk, so like this, whatever, slides, fine. Having traversed distance L is equal to 50 centimeters along the horizontal plane. Wait, what? Along the horizontal, but this is inclined. Okay, I think it means like the horizontal distance it covered is 50. So L basically. The disk stops. Okay, assuming the friction force coefficient K is equal to this thing for both inclined and horizontal plane. Wait, what? What do I have to find? Oh, okay, find the work performed by the friction forces over the whole distance, assuming friction coefficient this and both inclined and horizontal plane. Wait, what? Did they put some kind of figure? No, they didn't. Uh, both the Oh, I think there is a physical horizontal plane that they're talking about. Not just an abstract, like horizontal XY. No, it's an actual plane like this, and both of these have the same friction coefficient. I think that's what they mean. Okay, 30-degree, whatever. First, you go uh, slide with zero initial velocity down an inclined plane. Alpha is equal to 30 degrees horizontal. Having traversed the distance 50 centimeters along the horizontal plane, the disk. They didn't give us a figure. Why didn't they give us a figure? That would have made it so much better. Okay. Now how do I solve this? Look, it starts from zero, it goes to zero, yes. And it slides from here. So whatever the height is of this plane, that's what we look for, right? Okay, this distance along. Oh, okay. When it said this much distance along the horizontal plane, they're actually giving us what must have been energy that it amassed while falling this inclined plane. That makes sense, actually. Yeah, it actually makes sense, huh? Nice. So for it to go with L is equal to 50 centimeter, and the friction coefficient is given and everything. Yes. Okay. Just use v square is equal to u square plus 2s, right? So finally it's zero. Initially we don't know what it is, so just u square. It's like negative u square actually, and then that's equal to negative anyway, so it's positive. And then you got 2 times the friction force, so friction acceleration, if you will, which is just k times of g. And then that times the displacement, which is L in this case, right? So now you know what this is. So you can talk about, yeah, that makes sense. Yes. Okay. Think about it. And then you need to figure out how, I mean, what was this? Like, how high was that? Okay. Hmm. Well, while it's falling down, what is the work done in each dx length that it does? It's like dx times the friction force, so dot basically, right? So this friction force is just, well, k g cosine alpha. Yeah, that's the friction acceleration, but you get the idea, right? Oh, we could just use v square minus u square on this thing as well, right? Oh yeah. In fact, you know what? Like, let's define the kinetic energy upon mass, right? To be something else. I don't know, like half v squared. I want that to be some new term. Just calls k upon m, whatever. The thing is, half multiplying by m, just get the thing, right? So the kgl, this is the energy that it originally had, and then it lost it. So the work done by friction was against it and was equal to kgl. Yes, and over here it initially had zero. Finally, it had this thing. So half u squared is also the work done by, well, the gravity as well as the friction. So what's let's say it had gone with a length, I don't know, h. Yeah. So half u squared is equal to, you'll just have, or in fact, no, let's just call it L dash or L naught. L naught is better. And then this is H. So kg L naught, right? But in fact, there was somebody to support. Okay, that's not correct actually. It's supposed to be negative kg L naught because this was opposing the motion and then it increased. So yeah, negative kg L naught and then plus mgh because that was supporting the motion. So mgh, this is gh basically. So gh, which is gl naught sine alpha, that should do it. But look, both of these are the same, so it just goes like kgl plus l naught, which is basically the work, the negative work done by the friction. That was just gl naught sine alpha. Cool. So just put that over there. Oh, but we don't know what l naught is. Uh-oh, that's not good. Don't know what l naught is, then you're stuck. All you know is just L. You need to somehow figure out what L naught is. Oof. Well, actually, it's not that bad. You know, you just divide the thing and get that somehow. Okay, actually, yeah. First, what you actually have is KL plus KL naught. Or I just go with it. So this is equal to. Why is this so complicated? 1 minus k, sorry, no, sine alpha first of all, because yes, sine alpha minus k, and that means L naught. So now you know what L naught is, and really all we are looking for is just g L naught sine alpha. So now we can write that in terms of L. So this will just be equal to g sine alpha times kl upon sine alpha minus k. That should do it. That's our answer. Huh? So kg, oh, it should be sine alpha, sorry. Why is this alpha alpha? So it's kg sine alpha times L upon sine alpha minus k. Yes. Now let's see what this is for this particular case. K is it k? 0.15 and alpha 30 is like sine alpha is just 0.5. So 0.5 minus 0.15, that's 0.35, I think. Yes, so 0.35, huh? So like 0.35, sorry, 0.15 upon 0.35. That's what this k upon this thing is. Yes, 15 upon 35. It's like 3 upon 7. So 3 upon 7 into g, which is around 10. Sine alpha is just 1 upon 2, and then that times the length. 50 centimeters is just 1 upon 2 meters. That should do it. So this is like what? Oh, you could just use 9.8 because that is a better thing to use in these conditions. 9.8 times 1 upon 2 times 1 upon 2. Now, yeah, it's just 1 upon 4 basically, and then it's like 3 upon 7 into, well, it's like 4.9 upon 2 in that case, right? So 4.9 upon 2, and then just 0.7 upon, oh, that's like, okay, so it's just 2.1 upon 2, which is 1.05. There we go, that's our answer. So this is just 1.05 joules. Actually, it should be negative, but whatever. You know what? Yeah, whatever. Just put negative. Just put negative over there. Yeah, that should do it. So 1.05 is just negative 1.05. Okay, next 123. Okay, two bars M1 M2 connected by non-deformed light spring rest on horizontal plane. Have I seen this before? I think I have seen similar questions once. Okay, M1 M2 whatever. Coefficient of friction between the bars and the surface is equal to K. Okay, what minimum constant force has to be applied in the horizontal direction to the bar of mass M1 in order to shift the other bar? Huh? Wait, constant force. Okay. Fine. So like this should start shifting, and then there's this thing that's holding it together. Shift the other bar. Uh, think about it. It's a constant force that you have to apply. Minimum constant force, of course. But then what would that be? Uh, come on, think. Like that will do some kind of work, and then there's this friction, and this is also doing some work. Or you know, you could just do it the normal way. You got kx, right? So as it's moving, you just got kx in this direction on this guy, and then you got this this force. You also got friction as this is moving. Yeah. Okay. And it's like, okay, think. If it's not moving, okay, this is this kx on this direction, and then your kx should always be less than or equal to so m1 kg, so that this does not move, right? It's a constant force. Wait, if it's a constant force, then while this thing is moving, what will happen is that it will just, yeah, put some energy in there, right? Some kind of energy. Uh-oh, that's not good. Want the minimum current, right? So that this will happen. Probably. Come on, think about it. I mean, okay, once you have this in the I mean extreme process like that, yeah, I mean this kx whenever it becomes equal to m1 kg, this will start moving, right? So whenever that happens, up till that point, this will have gained some kind of kinetic energy. And so what do we expect? I mean, should it just start by I mean dividing the momentum equally? No. This will start accelerating slowly, right? There will be some constant acceleration, yes, but it will not gain velocity directly. That's not what's happening. Like, yeah, because if it had to happen, it would have happened already, right? So, right, and the same friction force. If I just keep using that friction, sorry, if I just keep using that particular force and it's at critical and then it's just barely moving, that makes sense. Yeah, that makes sense, of course. Then what's with the constant force thing? If that kinetic energy is not actually important, uh, how is this in work energy principle? Yes, it will give some kinetic energy. Yes, that's very true. Well, it will just come on. We'll figure out when it does not move, right? So for what values of this force this actually does not move. Uh, oh wait, it's like okay, it's like SHM, right? So there will be an equilibrium position. It's originally at its you know like at the extreme position, and then it starts to oscillate. That's what's gonna happen. Oh, okay. Now I'm starting to understand. And the maximum acceleration, if it does not move throughout the motion, then the maximum acceleration, right? This guy, if this does not move, maximum acceleration, so it's like some equilibrium position over here. Maximum acceleration will be when this is over here. Exactly. At that particular point, its velocity is zero, right? It has gone some k distance and whatever. Sorry, some x distance. Yes, and this force has done some kind of work on it. Yeah, this friction that has done some kind of work. Oh, okay. So originally it's oh sorry, this should be our x. That's right. This is not x, this is x. Because it's L naught, the original length. Now x times whatever friction force was there, so m1 times k times g. Sorry, m2. This is m2. Oh wait, okay, you are applying this to M1, so it should be 1, it should be 2. So this is M1 kg, and it should be less than or equal to M2 kg. Right. So, wow, very weird. Hey, okay, actually you can figure out what this should. No, there's friction. Uh-oh. There's friction right there. There's a problematic thing. It's not good. Um, yeah, we know it's gonna do SHM, but it's something like damped SHM actually. Right. So once it goes over here, it just loses the opportunity to pull this anymore. So once it reaches there, it should have been pulled already, right? So we'll find a critical condition when it does not pull it, even when it has reached at the extreme position, right? Because this is when the force is the maximum. From there on, it's gonna damp the SHM, and that's why, yeah, that's problematic thing. It's not normal damping because this friction force, I mean, it's not dependent on the velocity, right? But it will damp it. That's what we know for sure, right? Yeah. Wow, this is weird. Okay, so when it reaches at that extreme position, so this is X amount of work has been done. Friction has done this amount of work, right? Actually negative, of course. Then this spring has done some amount of work, just half kx squared negative on this guy. Yeah. This force has done some work, so F times X, that has to be equal to 0, because we will just say, okay, over here its velocity is 0. So this is the farthest away that it could get, and there's only friction force pushing it forward. There's no yeah, other than that, there's no force that's helping, not okay, there's no other retarding force. There's just friction and this spring force, and this is pushing it forward. These two are pulling it like that. This thing is increasing, that's the main thing. So after a certain point, this guy has to stop, right? Assuming that this does not move. So at that point, wherever it stops, you will just have the maximum X value. Because after that, I mean, right, after that it will come down over there. So yeah, let's figure out what this X should be such that this becomes 0. Yes, this it just like F is equal to M1 kg plus half kx. That should do it, I think. So now you have what X is. What's the acceleration will on sorry on the force on M2? What's that force? It's just kx, right? So what you're saying is like 2 times of F minus M1 kg. This thing is equal to kx. That should be less than or equal to M2 kg for this to not move. Yeah, and whenever that is not followed, it will move at that point or before that, right? So from here you can figure out what the minimum force should be. So actually it was work energy theorem. Yeah. Okay, now we got it. So force should be, I mean, less than or equal to M2 kg upon 2 plus M1 kx for it to not move. So whenever it's equal to that, that's the critical condition. I guess this makes sense. Yeah. That's what it is. Okay, start it down. So kg into M1 plus M2 upon 2. This is very unsymmetric. Why is this M2 upon 2 here? But whatever. This is what it is. Next, 124. Oh, okay, we have to calculate it. Sorry. No, we don't. They didn't give us anything, any values. Okay, 124. A chain of mass something and length something rests on rough surface so that one of its ends hangs over the edge. So, sorry. Something like that, huh? This is the table, okay. The chain starts sliding off the table all by itself, provided the hanging part equals 1/3 of the chain. What will be the total work performed by the friction forces acting on the chain by the moment it slides completely off the table? Hey, so if this is like infinitely deep, right, or at least deep enough for it to completely accommodate itself, right, so the whole chain can fall actually. Yeah, right. So, oh, okay, okay, understanding what's happening. Just gravity doing work. Yeah, that's not important. Just want the frictions for frictions work. Yes. So just this friction acting in this direction times the displacement. Well, okay, so dx. This thing is 1/3 of that. We just call this thing as x, and this will be L minus x. Okay, and well, there is gravity acting on it. Yes, uh, and then there's this normal force acting on it. Normal force must equal gravity. No, 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 not all of the time. That's not necessary. Oh god, this is bad. Okay, there's gravity in this direction. Man, the friction force changes with time. Uh, okay, this is not good. Okay, but for each element on this chain on a table, you can say that yes, only the normal force, the only normal force that it actually needs is, yeah, like there's only tension. There's only tension that can be there. Only normal force on this is this guy's mass times gravity. It's not anything more than that or less than that. I guess that's how it's gonna be. So there's this tension, yes, on this complete thing, and there's this tension. So over here you have a normal force acting in that direction and whatever. But yeah, that's just a small part, right? Okay. This is complicated. Normal force don't do any work anyway. And yeah, so throughout this, the normal force is just mg. It's not anything more. Yeah, and throughout this, the no, this is not there. Okay, this guy is accelerating. This the tension force that is making this little part accelerate, not the normal force that is making this part not accelerate that fast. That's not happening. I mean, there is this tension force that is making that happen. Yes, but there's not just normal force. Actually, in the end, it is the normal force that does it, but it's acting over here, not over here. So it's just one little part that does it. That makes sense, right? Or does it not? But this is also part of the table, yeah? So then, oh god, okay, this is not good, not good. Oh god, this is not good. Right, there's also going to be friction throughout here. And then because the normal force is so big, well, that times coefficient of friction, it's still considerable. So, oh no, this is not nice. Uh-huh. Now what do we do with it? Uh, this guy's velocity is, oh, it's increasing and everything. And but this is to actually figure out the friction, we have to figure out the normal force at every moment. Yeah. But how do we do that? Center of mass is falling down. It's tension that's pushing it in this direction. So you could just make this little part disappear. Okay, no, that's not good. That's not correct. You would think of it as a, I don't know, pulley, right? So whatever tension is on this thing, same kind of tension is going. So maybe this part is like very small or something. I don't know. Then it's just normal force is in this direction, and yeah, because so the tension force on this thing, both must be equal. Yes, because otherwise what will happen is as this as this part moves, if these are not equal, then the inequality causes work to be done on this small part. The normal force is not doing any work, and the friction force might be doing work. Okay, that's not good. What am I doing? This should I just approximate the like this part only? Should I do that, or should I take this into consideration, because that probably is working, right? It has to. Subtension force pulling in that direction. What am I doing? Think about it. The friction force, in fact, also acts in the vertical direction, I think, because look at this curvature. Normal, I mean, it's tangential, right? So it's gonna act like that. So actually, even the friction force is involved while talking about the force analysis. That probably is not the way to do it. I think work energy theorem is the only way to figure out what's happening. Normal force is not doing any work. Yes, gravity is doing some work. We don't know what finally the kinetic energy is. That's the main problem. We don't know that. Moreover, we don't know what the normal force is at any moment. And moreover, like also it changes because of this curvature. So it's a sharp change, right? Okay, let's, instead of doing that, just say that the friction force is just limited to this little region and it's not over here. If that happens, then the friction will not be upward anymore. Yeah. Then we could say that yes, these tensions must be equal, because otherwise they will do work on this part, and that will increase this part's kinetic energy, right? Yes, but I mean its mass is, well, infinitesimally small. Yeah, so the power it receives that is complicated. I think, yeah, this guy's mass is so small, so it's like dm, so half dm v squared, a change in that thing, right? So basically dm v dv, so it's two differentials, right? Actually the time derivative is like dm v dv upon dt, and then dv upon dt is a finite quantity, so dm times a finite quantity, it's going to be infinitesimal, and that means that the power received by this guy is actually 0. But for that to happen, the tensions must be equal, because yeah, like the tension forces, the difference of those, that times the velocity, that's the power, that should be 0. The only way for this to happen is that these tensions must be same. Yes, and what that means is, well, now we can do it. It's just going to be T upon whatever this mass is. So this mass is proportional to L minus X is equal to, so this is the same tension over here, right? This whole thing goes with the same acceleration, because string constant. So what that means is this is just equal to G minus of T upon X, because proportional to X. Actually, it should not be G. Okay, whatever. Just call this like mu times this. So mu here is the linear mass density or whatever. So it goes over here, since T upon mu, that times of, well, X plus L minus is just L upon X times of L minus X is equal to G. Now once you figure out what this tension force is, you can kind of figure out what normal force over here should be. I mean, that's actually not even important. All we need to know is this. Wait a second. That normal force, oh, this guy is only moving in this. Okay, this is just, fine. So with this approximation, you can just get rid of this upward normal force, right? Because that's not in the equations anymore. There's no friction. It's not doing work. All you care about is normal force on this little part, which yes is just upwards normally. Yeah, of course. So it's the normal condition. I'm saying normal for so many moments though. Yeah. Now this makes it very clear that you can figure out what the friction should be. It's gonna be K times the mass of this thing, and that times L minus X upon L times G. That's our friction force. And now this thing times dx because it moves dx, right? Yeah. Then integration of this thing x goes from, well, 0. Actually, no, it's not 0. It is 1/3 of the original length. So it's like L upon 3 all the way till, yeah, all the way till 1. So L basically. Now, what we can do is that instead of writing like that, we'll just write as 1 minus eta, and here eta will be a variable quantity. So this will go from whatever eta it originally was to 1, and then dx can just be written as LD eta. Yes, makes sense. So it just becomes kmgl, and then integration of this thing just eta, it goes from eta to 1. So like, yeah, 1 minus eta. Is this eta or what is this? Mu? I don't know what this is. I think it's mu. What is eta like? I don't know. I just call it eta. Yeah. Then minus this thing squared upon 2. So it goes from 1 to that. So like this. That should do it. Cool. So this work done is just kmgl 1 minus this guy. Then you got, just take that 2 side. Now it's gonna be 1 minus this thing upon 2, so it's just 2 minus that, so 1, and then 1 minus eta. Still calling it eta. Yes, this thing. So there we go. kmgl plus this guy squared, all of that upon 2. That's the work done by friction. I know we would have done this normally as well, right, just by assumption, but I wanted this to be perfectly clear. It's the first time I have ever encountered this kind of problem. Now seriously, I mean, like, I don't encounter these kind of problems all of the time, right? Mostly mostly you just get the friction to be 0 everywhere. But sometimes when there is friction, I mean, yeah, isn't this a puzzling question? That what would happen if, as it was falling down, there was still some part that had that friction? What if that happened? How would you figure that out now? Right? That was something that's worth discussing, right? Anyway, now we got the thing. Now we got a formula for it. Just plug in numbers. Mass is given. So friction coefficient is just, what's the friction coefficient? Huh? It's not given. Oh. Oh no. But why? Why is this not given? You don't know how to figure out the kinetic energy change unless you figure out the friction, and you can't figure out the friction unless you know K. This is just not doable. Oh God. What if it's just slowly sliding off? It just said it starts sliding off, right? Yes. We don't know what velocity it achieves. Oh, this is really bad. Okay, fine. I'll see this in greater detail later on. Just skip this for now. 125. A body of mass m is thrown at an angle alpha to the horizontal with the initial velocity v naught. Find the mean power developed by gravity over the whole time. of motion of the body and the instantaneous power of the one. Okay, body of mass m from an angle alpha to the horizontal with initial velocity v naught. Find the mean power developed by gravity, okay, over the whole time of the motion. Find like complete work done. Okay, I mean the complete work done is zero. Ha. Yeah. Yeah, and instantaneous power of gravity is a function of time. So like first part is just really easy. So average power, right? Mean power developed by gravity, of course. So average power is zero, and instantaneous power, right? Instantaneous power as a what? As a function of time. Fine. So its velocity, it varies as vx and vy minus gt, right? And then the force on this thing is just 0 comma negative mg, right? So they're dot products, and that will us the thing. So it's going to be mg into gt minus vy. So vy is just v, so whatever initial velocity it was, v naught, and that times sine of alpha. That should do it. So instantaneous power is just this quantity. That's sufficient, I guess. Oh, okay, this. Right. 196. A particle of mass m moves along a circle of radius capital R with a normal acceleration varying with time as this thing, where a is a constant. Find the time dependence of the power developed by all the forces acting on the particle. Normal acceleration varying with time as this thing along a circle of radius R. Okay, where a is a constant. Wait a second. Okay. So its velocity, you just gave us how the velocity changes. Like v squared upon r is going to be this thing. So v squared is just r a t squared. That's all you are saying, right? Power developed by all the forces acting on. I mean, just tangential forces times the velocity. I mean, yeah, that's all it is. That's the power. Tangential force, not acceleration. Mean value of all of this power averaged over the first 3 seconds. Oh, wait, we don't even need to do that because they already gave us the kinetic energy by giving us v squared. Wow. So half mv squared, the kinetic energy is basically just half mrat squared. So half m rat squared. Yes. What are we doing with it? Yeah, just want, so initially it's 0, right? Yeah, at t equal to 0, your acceleration was 0 normally, and that means your v was 0 as expected. So average over the first t seconds is just the kinetic energy that it gained upon t. So average power is equal to mrat upon 2. Huh, I like it. And instantaneous power is, so just the derivative of this thing with respect to time, right? Which is going to be mrat times, well, I mean, just that actually. So it's going to be mrat. Cool. This is awesome. Next. 197. A small body of mass m is located on a horizontal plane at an angle O. Horizontal plane at an angle O. What? Okay, so at the point O, yeah, the body acquires a horizontal velocity v naught. Okay, mean power delivered by the friction force during the whole time of motion. The friction coefficient is this. Wait, I mean, we know it's just gonna stop in the end, so just half mv naught squared. What is this? Why did they give us anything about it? Mean power developed. It's just the okay. So we need a time. We need the time required for this to happen. Yeah, that's how it will be. So it's just a, I mean, constant deceleration on it. The maximum instantaneous power developed. Fine, let's do this thing. Let's do this thing. It's got v square minus u square, which is like v naught squared, is equal to 2as. In this case, it's going to be negative of 2. And then what, like, acceleration is just k times of g. So, yeah. And that's the displacement. So, call this x. That should do it. Or maybe not. Oh, why am I doing this? This is not helpful. I should have not have done this. The thing is, I should have used v is equal to v naught minus k g times t. Yes, that would be the more useful thing. So as it goes from v naught to 0, the time required is just v naught upon kg. Yeah, so you can figure out what the instantaneous, what the average power should be. So A is actually not that hard. Yeah, it's going to be half m v naught squared upon this thing. So v naught upon kg, yeah, cancels. So it just becomes m v naught kg and then half of that. Okay, cool. That should do it. Yeah. And B is maximum instantaneous power developed by the friction force if the friction coefficient base is what? K is equal to alpha. Are you serious? Fine. So you still have this kind of equation that, okay, what is it? It's just negative dv upon dt is equal to, wait a second, d max. Oh yeah, like it changes with x, right? All we want is just the force times the velocity. How about this? Instead of doing this, we can just use this guy, that v squared. Okay, no, let's not do that. Yeah, let's do it. You can figure out what the work done is in x amount of distance, and then from it you figure out what v is. Okay, this is helping. This is not helping. We'll have to figure out v, otherwise it's not doable. So v squared minus v naught squared. Yeah, that's how we'll have to do it. Wait, we just want the maximum speech power, and let's do it. You know what? Let's do it. That's supposed to be equal to integrations, like negative 2. Let's see, it's supposed to be k m g. Okay, m is not this. Like negative 2g integration of, well, this thing. Well, alpha is also out. Negative 2g alpha, and then integration of x dx, I guess. Yeah, that is how it should be. Negative 2a. So for a, you would just need g times k. Yes, and that times s, which is dx. So g times k is just alpha x, and that's why this thing. Right, as it goes from x equal to 0 to some other x. So this is well, put 2 over there, so maybe x squared. So it's only negative g alpha x squared. There we go. That's the friction, huh? I mean, that's the work and mass friction, or maybe 2 times of that upon mass. You get the idea. And once we have this, you can just figure out what velocity should be, and then from there you can, yeah, this will be doable in that case. So we will get this as a function of x. So just get v is equal to square root of v naught squared minus g alpha x squared. Once you have this, so try the force, and the force is just mg, like negative, but you get the idea, and then g times of k, which is alpha x. Yes, that should do it. So this times velocity, so this times square root of v naught squared minus g alpha x squared, but negative of all of that. That will be the thing. And this should also in fact be negative. And there we go. Got the thing as a function of x. Because that's how they were expecting this to be. Or do they want it as a function of time? Oh, okay, they just want the maximum, like a value. They just want the maximum value of this thing. Ah, oh, all right. So how do we figure that out? You can just say that x is v naught upon square root of g alpha times, like sine of theta or something. Then yeah, this whole quantity will just become negative mg alpha, and then instead of x we just put v naught upon square root of g alpha, and then from here you just take a v naught out, and it will be sine alpha, sorry, sine theta and cosine theta. Now this thing has the maximum value as half. So there we go. This is the maximum value, so we just don't need to put this in there. Yeah, since we figured this out, we'll just keep it as a separate result, but this is actually what the value should be. So first of all, cancel some stuff out, which is square root of g alpha right there. So it's supposed to be negative m v naught squared upon 2, but that times square root of g alpha. Huh, weird, isn't it? Yeah, that's like a power, but how? It's alpha times x. That's what k is. So k is unitless, so this should be in meter inverse, and then g is in meter per second square, so this times meter inverse is just per second square. So this yeah, the second inverse comes out, and then you got this thing is just energy, and that upon second inverse, and yeah, that's power, and that's good. And we can also write instantaneous power is equal to, as a function of x, it's just equal to this. Well, actually, I mean, okay, the maximum power, that's what we're looking for, right? The thing is, this is negative, so maybe the maximum power is supposed to be 0, right? That could be the thing. So at the very start, it's not 0, because actually no, it is 0 because alpha x is 0, right? So at the very start it was 0, I guess, and at the end as well it was 0. So maybe that is the maximum power, because otherwise it's just negative. Yeah. Anyway, this is how it is. So you got 127 done. You need to calculate it, right? Well, b, I'm just gonna leave. Write down the magnitude actually. Fine. And for a, we'll have to calculate this thing. And since they just want the magnitudes, we'll just put this as the answers. Now let's do it. Mass of, so 27. Mass is 1, k is 0.27, so half, 1, 0.27. Velocity is 1.5. Yeah. That times gravity, I think it's gonna be 9.8. Is that how it's supposed to be? Let's try to do it. So this can be done as 4 point. Actually, no, just take it as 10 because, yeah, 10, 5, cool. This is like 0.81 times, like 0.5 times 5, so 2.5, something like that. Okay. So 2.5 is like 5 upon 2. So this times, yeah. Yeah, that should do it. So it's just gonna be 4.05, and that upon 2, which is just 2.025. That's the thing. So this is approximately 2.025 Newton per second. It's the power. Next, 128. A small body of mass something moves in a reference frame. What? Reference frame. The F got cut. Okay, frame rotating about a stationary axis with a constant angular velocity omega. Okay, rotating about a stationary axis. Oh, okay. What work does the centrifugal force of inertia perform during the transfer of this body from an arbitrary path from point 1 to point 2? Okay, the rotating axis. I mean, no, it does no work. Centrifugal force is, I mean, pseudo, so why should it do any work? Moves in a reference frame rotating about the station axis from uh, oh, I mean, you want with respect to the rotating frame? I think that's what you mean. So then it just says, okay, fine. In that case, when we take the point of view of the rotating frame, the centrifugal force becomes very much real. Okay. Point 1 to point 2, which are located at distance r1 and r2 from the. Fine. So the vector going from r1 to r2, it's got some tangential path. Yeah. Right. I mean, you should not think of it as vector, but as a path basically. So instead of going from here to here directly, we could break this, right? So you could break this as some radial plus some tangential component, right? Of course, something like that. So then it's just basically like this whole tangential path is not used, and it's just the difference of the radii, and that thing times the centrifugal force. That's our work done. Of course, outward. Okay, cool. So I mean that's in the frame of the in the rotating frame. In the space frame, there's no such thing as centrifugal force. So it's gonna be what? M omega squared r. That's the centrifugal force. Yes. Oh yeah. I mean, okay, wait. This thing is also just moving with some different angular velocity actually as it goes from here to here, right? So I mean, okay, that's not involved in the centrifugal force itself. It's from the Coriolis force that it comes in there. So you can just ignore that, you know. Yeah, just ignore that. So just m omega squared r. That's it. That's the whole thing. Okay. So what do you want? This thing. So like integration of this thing as it goes from okay, this times dr as r goes from r1 to r2. That should be a thing. Yeah. Yes, that's how it should be. So it should just be equal to m omega squared r2 squared minus r1 squared upon 2. Yes. This is the work done. Yeah, it's actually very simple. I don't think it should be that simple. It is. Half m omega squared that times r2 squared minus r1 squared. That is the work done. Well, let's check the units. Omega r2, yeah, it's just v squared, so no big deal. So this is gonna be what? Right, 128. They gave us the things. So half of mass is just 0.1. Okay, that times omega squared. So omega is 5, so 5 squared, and then r2 squared, which is 0.5 squared, minus 0.3 squared. So it's going to be basically 0.5, 0.4 squared, right? Yes. So basically just 0.4, 0.16 is better, I think. Or no, 0.4 square is better because we can write this as 5 to 0.4, that thing squared. So basically 2 squared. 4. 4 upon 2 is just 2. So 2 times 0.1 is just 2. Sorry, 0.2. So this will be the answer. Next. 129. A system consists of two springs connected in series and having the stiffness coefficients this. Find the minimum work to be performed in order to stretch the system by delta L. Stiffness coefficients K1, K2. Okay. Find the minimum work to be performed in order to stretch this system by delta L. I mean, come on, really? So the thing is, like, both of these springs will have the same tension through them because these probably are massless or something, I don't know. And if you want to keep it like that, stretched like that, then yes, these will in the end just come down to having the same tension. So since the stiffness constants are like these, the inverse of these constants is what lengths they should have, right? Because k1 x1 is equal to k2 x2. Yeah, so we know like k1 x1 is equal to k2 x2. And what do you want? Find the minimum work to be done in order to stretch the system by delta L. Yeah, so just figure out what x1 x2 is. It's all the same. Technically k1 x1 squared and whatever. All right, fine. I don't like it. What should I say? Just let this thing be. I don't know. What am I doing? Well, we know like x1 plus x2 is basically what delta L is. And what we are looking for is the work, which is just half k1 x1 squared plus half k2 x2 squared. How do I get to that fast without doing anything? Can I do that? I don't know. But we know that k1 and k1 x1 and k2 x2 are the same. So in fact, we can write this as half k1 x1. Well, that times of x1 plus x2. Weird, but that's how it is. So it's like half k1 x1 that times delta L. Wow. Now we need to figure out what x1 is and we'll be done. So let's multiply this thing by, I don't know, k2, or in fact even better, k1 k2. So then it will just be k2 and call this whole thing as, I don't know, f. So this will be k2 times of f plus k1 times of f is equal to delta L. So you got it. F is just delta L upon k1 plus k2, and just put that into here because this is f. So this will be half delta L squared upon k1 plus k2, which is to be expected, right? These spring constants add up. Well, actually that should not happen. No, these spring constants, why do they add up? But this is the work done, huh? Wait, what? That can't. Oh, sorry. It should have this times k1 k2. Okay, that's how it's gonna be. So this times k1, which is to be okay. I get it. When these are in parallel, they add up. When these are not in parallel, this thing happens: 1 upon k1 plus 1 upon k2. And yeah, the same formula apply to this. So half kx squared, you get the thing. So it really is just k1 k2 upon 2 times of k1 plus k2. And that times delta L squared. That should do it. Okay. So that's 129. Okay, and they didn't give us any values. No? Then that's it. Okay. 130. A body of mass m is hauled from the Earth's surface by applying a force F varying with the height ascent as F is equal to 2a by mass. Okay, fine. A is a positive constant. Find the work performed by this force and the increment of the body's potential energy, gravitational field of the Earth over the first half of the ascent. So the work done is just the increment, right? Because it's just hauled. Wait, what does hauled mean? Is it like it's at 0 first and then it's going up and then it's 0 again, or not? Or is it that the force is applied constantly? Uh, okay. A y minus 1 times mg. So A is a positive. So as your y increases, this force also increases, right? But that would mean that as we go up, in the end, I mean, it just flies up physically. Uh, yeah. And initially, when y is 0, this thing is negative, so it should technically not do anything. It just compresses further into the earth. Send y like this. I don't understand what is happening. First half of the ascent. Okay, this is very suspicious because it's got a y minus 1. And at y equal to 0, it's negative 1. And no, that's not good. Oh, wait, this is g vector. It's not. Okay, that makes sense. Fine. So actually, the thing is like force is just, so it's upwards, yes. And basically, it's just 2 into 1 minus ay times mg. Right. This g vector makes it negative. That's why this is the way it is. All right, cool. Um, yeah. So the complete force on this thing, or maybe we just do, I mean, integration with respect to y to find out the work done by the force and work done by this mgh thing, and figure out the velocity from that. Find out the work done performed its force over the first half of the ascent. So you have to figure out time dependence as well. Oh, this is bad. Fine, so you need to figure out time dependence. You just have to do the proper analysis for this. Is this force actually like, okay, first it will increase, and then at some point it start to be negative. And from here it will, yeah, go down. Okay, it's 2 times of that. So basically I find as mg is the total force, which will be 1 minus 2 ay times mg, right? So all we need to figure out is at what time will the velocity become 0. Yeah, since the force, so this upon m, that's going to be the acceleration, and that's so that's our acceleration in the upward direction. Shit. Okay, so v square minus u squared is 0, is equal to integration of this acceleration times dy basically. So that's going to be y minus ay squared times g. Yes, actually 2 times of that. Yeah, so 2a's is for this thing. So 2y into 1 minus ay that times g. So now you know how the velocity changes. Yes, that's good and everything, but this is not sufficient. No, what we want is the time required for this to, yeah, because half of the ascent, it's got to be just that. First half of the ascent, it has to be like that. Or do they mean just the first half distance of the ascent? Because I don't think we can actually figure out what the time should be, or can be. I don't know. I have no idea. Right, you got velocity at the square root of this thing, and then you gotta do integration of dy upon v to figure out the time. And it's just really stupid. It's not helping. Like y into 1 minus ay. That kind of integration is not easy to do. You want something that is easier to do. Come on. Don't want something like that. What do they mean by half the ascent? Do they mean a distance? Probably. So if this is 130, yes. First half of the ascent. It has to be the time required, yes. Half of the time, because what else would it even mean? Well, actually, wait a second. You know, at some particular, y value, this complete thing will become 0, right? And after that, it just starts going up. And then, okay, it goes down. Fine. No problem. Something like an SHM, maybe? Yeah, something like an SHM. That's what it is. Yeah, right. So, when will this force, the total force, be 0? That happens when y is equal to 1 upon 2a, right? And let's just call y dash to be y minus 1 upon 2a, right? So for any general y. Then we can just write y as y dash plus 1 upon 2a. So then this whole thing just becomes, well, that 1 minus 1 is 0. So it's going to be negative 1 upon 2a y dash. Sorry, what am I saying? Negative 2a y dash. And that's our expression. Fine, just use w for this. I hate using w, but whatever. That's our acceleration. Oh, that times g. Sorry. Yes. So now it's just SHM basically. So yeah. And initially it was at the extreme position, right? The negative extreme position. It's going up. So it has an angle. I mean, the phase angle is, I think, negative pi upon 2. Yeah. That probably makes sense. So you can just say y is y, the y naught value. Yes. So 1 upon 2a, but that's when this happens, right? So 1 upon 2a, and then sine of wow, this is complicated. Negative pi upon 2 is there, right? Oh, it should not be y, it should be y dash, but you get the idea. And then you got, well, square root of all that stuff. So square root of 2ag, that times time minus pi upon 2, that should be doing it. So y dash is just negative 1 upon 2a cosine of square root of 2ag that times t, right? Now you have this. Cool. So find the work performed by this force and the increment of the body's potential energy in the gravitational field of Earth over the first half of the ascent. So it's going up. It will reach the other extreme at some point, right? And it will start going down. So till that point, it's ascent. So we want half of that. Oh, well, that's just when it reaches the equilibrium point. So it was also the half of the distance. That is, wow. Just wow. Right. This somehow works out. So it's just half of that distance. So just still y naught is equal to 1 upon 2a. Yeah. So you just need to integrate this force till y naught is equal to 1 upon 2a, and you will be done. Isn't that nice? Why did I do all of this? Right, this is not useful at all. So I mean, it's useful to actually figure out what time required is. Yes. And what do they actually want? Work performed, exactly nothing about the time is required, except the fact that half the distance is the same thing as half the time in this case. right? So integrating this thing to y, yes. Then it is plus 2y, and yeah, like 1 upon 2a, that's the midpoint. So just put that in there. Y naught is equal to 1 upon 2a. So 2y naught minus, well, a y naught squared, and that times mg. That is our work done by this force. Now the increase in potential energy of gravity, that is just y naught mg, right? So this thing is just y naught mg plus y naught minus a y naught squared mg, right? This thing is the change in kinetic energy, and this is the change in the potential energy. Yes. Now y naught is 1 upon 2a. Putting this in there, just get mg upon 2a, and then plus, so 1 upon 2a minus a upon 4a squared. So basically minus 1 upon 4a. So that's just going to be 1 upon 4a. So mg upon 4a. There we go. So finally, 130. Work done by force F is 3 mg upon 4a. Yeah, that should probably do it. Makes sense, I guess. Yeah. Yeah, that makes sense. And A just has meter inverse as a thing. So this is 1 upon is like meters. So Newton meters. Cool. Change in the potential energy of gravity due to gravity. That is just this quantity. So just mg upon 2a. And the change in kinetic energy is this complete quantity, right? This quantity, sorry, which is going to be mg upon 4a. Cool. This is it. So that's it. For now, I'll stop. I'll see you guys in the next video.